Okay, we're recording. So so I can play back the so your teachers can play back and see how well behaved you were. That's the only reason for doing it. No, I joke. That's not true. Judging by what you're wearing today in Kenya is quite warm because some days people come in with big jumpers and hats. And today you're in just shirts and jumpers. Well, it's presumably quite hot. Here it is 10 degrees. And cloudy. The UK is a very cloudy, wet, boring place sometimes. Okay, so here we go. Energetics. So I'm going to share my screen, I hope. And here we are. And last time we were doing something called Hess's law. I'll just okay. Hess's law. And Hess's law is, for some people, is quite difficult. The questions are quite relatively complicated, but they are worth many marks. So it was about saying that if you look at any reaction, to know the whole energy change, all you need to know is the difference between where it starts and where it finishes. So down or up, it doesn't matter. It doesn't matter how many steps there are in between. That is not important. And we did it via a silly example where we said about Nairobi going to Malindi and Nairobi going to Mombasa and Malindi. In other words, saying that the route 1 in this case and route 2 round the bottom are the same totals. So that's what we have to do. That's what we said. We would do it like that, just to make sure we started in one place and ended up in the same place. Sorry, at the same place, independent of the route. So we went on. Oh, sorry, I'm just going to move on a bit. We said the way to do it is to construct a diagram that includes the left-hand chemicals and the right-hand chemicals. This is one trying to find out the energy given out when methane, the chemical on the left, burns in oxygen to form carbon dioxide and water. And we found that energy is the same as going from methane down to carbon and hydrogen and up to carbon dioxide and water. How is it carbon and hydrogen here? Well, we are always given some data. Here is the data. And we are given C plus H2 makes CH4. Okay, that's there. And so I know then I can draw an arrow from CH4 to CH4 from C and to hydrogens. Okay, that's what I can do. And I can do the same sort of arrows up. And all I have to remember is that from Nairobi to Malindi is the same from Nairobi down to Mombasa and up to Malindi. In other words, I would have to change the direction of the yellow arrow. Can we mute, please?
Silver screen, kindly mute. Silver screen. Silver screen, kindly mute.
Thank you very much. Nearly. We have to hang on. Thank you. Okay. So then we moved on to bond energies. And we said that in this is the same equation. This is CH4 plus 2O2 turns into CO2 and 2 waters here, left-hand side to right-hand side. And this is what we call an energy profile diagram. And it is energy up the side, and it is time or progress of reaction or state of the reaction along the bottom. In other words, it is assuming that we are moving from the left to the right. What it explains is that the molecules on the left are going to have to be broken into the individual atoms. So at the top, we have 1 carbon, 4 hydrogens, and 4 oxygens. Those hydrogens are not meant to be joined. And then they recombine, making new bonds to make 1 carbon dioxide and 2 waters. And by adding up the amount of energy we have to put in to break the original bonds and then make the new bonds, we can find out the reaction. So then we had an example, which was dehydration of ethanol to ethene. The dehydration of ethanol to ethene, okay? And we were given a group of bond energies, and I'm going to show you this one. But here are the bond energies on the left-hand side, and you have to be able to work out how many you're going to break and how many you're going to make. And I gave you a simple way of remembering which are endothermic and which are exothermic. The thing to remember is Bendo, Mexo. Bendo, B for breaking, endothermic, and Mexo, M for making bonds, is exothermic. In other words, to break this molecule of ethanol on the left-hand side is going to be endothermic. We are going to have to put in energy to break this bond and this bond and this bond and this bond. So we add up all of those, and that will all be a positive number. The ones on the right-hand side, it will be a negative number. Okay, so this is how it works. So I'm looking at the ones which I'm going to break and the ones I'm going to make. So I'm going to break a carbon-to-carbon bond in the middle there, worth 347. I'm going to make a carbon-to-carbon double bond. That's worth more, and it's negative because it's making a bond exothermic. So I go through 5 carbon hydrogens on this side being broken, 4 carbon hydrogens being made on that side. So on this side, positive, on this side, negative. A carbon oxygen and an oxygen hydrogen on the left-hand side, and 2 oxygen hydrogen bonds on the right. Then we total it, and we find the positive is 3237 and the negative is 3203. And we put those two together, and the total comes out as, there we are, negative 34. So before we go any further, I'm going to give you an example where you can have a go yourselves, just to see if you can remember how to do it. Okay, so I'm going to give you the chance to have a go. Some of you may find this a bit difficult. If you find it a bit difficult, don't worry. Here it is. Here is propane, C3H8, and it burns with 5 oxygens to make 3 carbon dioxides and 4 waters. Okay. Now, it would be very difficult if I left it like that. So what I'm going to do is I'm going to show you the molecules. So if you are clever enough to do it without seeing the molecules, try not to look at this next slide. Here is the next slide. Here are the pictures of the molecules, which will make it easier to see how many of each bond you break. When I do this, if I am teaching my class to do this, what I normally do is I say you should put a line. If you draw this out, you should put a line through bonds as you break them or make them. So you can see here that there are 2 carbon-to-carbon bonds. 2 of these 347s are going to be needed. There are also going to be 1, 2, 3, 4, 5, 6, 7, 8 carbon-to-hydrogen bonds. Then there are going to be 1, 2, 3, 4, 5 oxygen double bond oxygen. So I'm going to give you a few minutes now so you can have a go at this calculation, and we'll see if anybody comes out with the right answer. We'll see how you get on. Okay, so anybody can have a go now. It's propane, which is used as a camping gas and is used for cookery. So it gives out quite a lot of heat, and the end answer will be negative. So for those of you who were not here before, you have to total all the bonds on the left, and they will be positive. And then you total all the bonds on the left, and they will be negative. and then you add those two numbers together. Have a go. See if you can do it. It would be good to see if you can do it. Have a go. Anybody can have a go. Every school here can do this, I think. So, Glory, what you need to do is to look on the left-hand molecule here, the propane, and say, all right, I need 2 carbon-to-carbon bonds to break. So that will be 2 times 347. So I take my calculator and I put in 2 times 347. And I get 694. So I write that down. Then I add up. I also have, if you look at propane, I have 8 hydrogen carbon bonds. Okay, each one of those little lines there is worth, according to this table, 413. So I take 8 times 413, and I add that to the 694 for those two. And then I add up 5 of the oxygen, double bond oxygen. Each one of those is 498, so it's 5 times 498. So I add up all of that. That is a good start. That would be worth 1 mark on its own. Then you do the same for the second set of chemicals. That will be a negative. And then I put them together. I will show you this in a minute. Have a go, Church Army. I think everybody should have a go. Don't wait for your cleverest student to have a go and then tell everybody. Please, it would be very nice if everybody had a go. It's the way to get better is to have a go yourself, not say, oh, well, David is very clever. So I have a number from Asharika already. Is that 13070? Is that? Oh, it's positive 3070. Ah, is it? Well, Asharika, good answer. But firstly, it cannot be positive because propane is a fuel. And because it is a fuel, it will give out heat. That would make it negative, okay? But 3070 seems a bit large for propane. So just check your maths, check your arithmetic. That's the thing which is difficult. For those of you who are struggling, I'm going to show you the next slide so you can see how to do it. So here's the question up at the top. I'm sorry, I'm slightly in the way. Here's the question up at the top. And here are the molecules. So the Bendo, that's what I'm breaking, and therefore it's endothermic, is 2 carbon to carbon. This is how I would add it up. I would say, hey, I have 2 carbon to carbon, 8 carbon to hydrogen, 5 oxygen, double bond oxygen. And then in the making, Bendo, Mexo making on this side, I have 6 carbon to oxygen bonds, double bonds, and 8 oxygen to hydrogen. Okay, so then I would put the numbers in. So there are the numbers. Okay, and that's how I would do it. Okay, so I'll leave that up in case people want to see how to do it. Has anybody got an answer? Anybody got an answer? Negative 287 from somebody. Negative 287, negative 287, possibly. Well, we'll see. Just always check your maths several times, okay? It's very important. Negative 490 in Asharika. Dandora is negative as well, but they're quite small numbers at the moment. You have to, this is about being very, very careful with the numbers, okay? Being very, very careful with the numbers. I'm going to go through it in just a moment. Anybody else got an answer? I think your teachers know. I'm pretty sure your teachers know. St. Mary's, have you got an answer? Come on, St. Mary's, you can do this. Oh, come on, have a go, man. Like, oh, we can do this. We can do this, St. Mary's. Ah, we have another answer. This, and let me just hold it there just a minute. Let me just pin and make it bigger. Oh, come on. Sorry, just trying to make the stream bigger. Up a bit. Sorry, you're showing me the beginning of your calculation. Up a bit more. Is that 2470? Close. You got some very good numbers there. Got some very good numbers there. It's not quite right for the total yet. Okay, let me go through it. Let me just go through it and let's see if it makes sense. So there's the equation up the top. There's the molecules. Let's look at it. So I think I've got 2 carbon to carbon, 8 carbon to hydrogen, 5 oxygen double bond, 6 C double bond O, 8 HO. I think where's that gone? Oh, I think 2 carbon to carbons will be 694. I think 8 carbon to hydrogens will be 8 times 413, 413. And that will then make 3304. Check it out with yourselves. Just check it. Then 5 oxygens will be 5 times 498, which is 2490. They are all then added together and are positive. On the right-hand side, I have 6 carbon to oxygen bonds. That's a large number because the carbon-oxygen bond is strong. That's C double bond O. Important that you see that. That's the 745, not C single bond O, not 358, but 745, and 8 hydrogen to oxygen, which are 67 each. If you then total those, we get that. Okay? So the total of the Bendo, the breaking bonds, which will be endothermic, that means a positive number, that will be 6488. If my maths is right, my arithmetic is right, I may be wrong, and 8206 on the right-hand side. So then I just add those numbers together. Positive 6488 and negative 8206. If you want to write down the numbers, there they are. So the total is negative 1718. People got close, but you need to be very, very slow and careful. So if you want to write it down, I'm very happy if you want to write it down. It's quite a simple calculation, but it's easy to get it wrong because we forget a number or pick the wrong one. From these tables here, if you pick C single bond O instead of C double bond O, you would make a big mistake. Okay, so we've started quite hard with quite difficult stuff. So let's make it a bit easier. So there's the whole thing. Anybody wants to take it down, but it will be recorded so you can see it anytime you want. All right. So I'm going to move on now. I hope that makes sense. Does that just, if you would be kind enough, please, everybody, just show me that it makes sense, even if you didn't get the right answer. So makes sense, doesn't really make sense, doesn't make sense. Okay, so everybody, just show me quickly. Everybody, Church Army, show me. Does this make sense? Church Army. Oh no, Church Army have lost their arms. Oh, it's so hard. Thank you, Dandora. Thank you, Ursharika. St. Mary's, you understand what we're doing? Cool. Okay. All right. Wamawini, do you understand what we're doing, even if it was a bit difficult? Silver Spring, do you understand what we were doing or not? Okay, that's good. Thank you very much. Okay, so I'm going to move on now. And we're going to move on to a little sort of a quiz. So here we have, oh, how do I get that? That's a bit. Can we mute, please? Mute, please. I think it may be Wamarini. I'll mute you. It's okay. Okay, in this question here, you have to choose the correct word. Could we mute, please? Thank you. We have to pick the right word to complete the sentence. Okay, so in other words, when a fuel burns, heat energy is given out. This means it is, and you have to choose whether it's an exothermic or endothermic reaction. So just look at it, talk to your neighbor about which one you think is right in each case. Don't bother writing it down, because if you can write down the bits that you're not sure about. Okay, you can write down the bits that you're not sure about afterwards, but just for the moment, just have a look at it. Just have a look at it, and I'm going to ask you to show me with thumbs and so on. Okay, so we'll just see. Don't bother. Don't necessarily write it down.
Kabiro secondary, kindly mute. Kabiro, kindly mute. Kabiro secondary. Mute.
Hang on. I've done it. The trouble is I can't do that when I'm sharing the screen, which is a bit frustrating. Anyway. Okay, so I'm going to be asking you to show me with your thumbs whether you want it for exothermic or endothermic, and we're going to go through the whole thing. Okay. So here we go. This is a little bit of a knowledge check, just a checking that everything is going okay and we know what is happening. Okay, so here we go. When a fuel burns, heat energy is given out. This means it is is it exothermic or endothermic? Show me, every student, please. Just show me with your thumbs. Exothermic up, endothermic down. Come on, Wamini. Come on, Mathari. Come on, Kabiro. Have courage. Come on now. Exothermic, when heat is given out, is it exothermic or endothermic? Exo, endo. Okay, more people showing me up. Up is correct. Why? Exit is the way out. If heat is given out, it's exothermic. Well done, Wamuini. Okay, so just about everybody got that. So the right answer for that one is exothermic. Some heat is needed to start the reaction. This is called either activation energy or the reaction energizer. Okay, activation energy or reaction energizer. So first one, activation energy or or reaction energizer. Which one do you think? Show me. Activation energy. Dandora really sharp on this. Come on, everybody else. Do you think it is called activation energy or do you think it is called reaction energizer? Come on, Kabiro. Come on, Glory. Take part. Come on, Mathari Mixed. You can do it. Mathari Mixed all walking out. Oh, well. Church Army, what do you think? Oh, no. No. Okay. It is called activation energy. If you did not know that, you need to write it down. The energy needed to start a reaction is called activation energy. The next one. In an exothermic reaction, the products Are the products at a lower energy or a higher energy? So does it go from reactants down to products, or does it go from reactants up to products? Are the products lower or higher? Lower or higher? What do you think? So are they higher or lower? What do you think? Osharika are thinking down, Dandora thinking down, Mathari Mixed going down, Gloria not quite sure, Kabiro, what do you think? Down or up? Well done, Wamuini. Well done, Wamuini. So everybody right so far. That's very good. I'm very impressed. I'm very pleased as well. So the answer is the products are at a lower energy. It drops from reactants to products, which is energy given out. In an energy profile diagram, the vertical, the y-axis, is energy or progress of reaction. Energy or progress of reaction. Energy up, progress of reaction down. Energy up, progress of reaction down. What do you think? Up the y-axis. Dandora think it's energy. Osharika think it's energy. That should give you a clue because those guys are normally right. Wamuini, Church Army, what do you think? Up the y-axis. It's energy. It is energy. The answer is energy. Okay. The last two bits. The overall energy change, mute please. The overall energy change is the difference between either the reactants and the products or the top of the curve and the bottom of the curve. Is it the difference between the reactants and the products, or if it's one of those with those like that, is it from the top of the curve down? So reactants and products. Mute, please. Mute, please. Thank you.
Silver Spring, kindly mute. Silver Spring.
So, is it the reactants and products, or is it from the top of the curve and the bottom of the curve? Reactants, products. St. Mary's at the back. Somebody is saying the top of the curve. Wamuini goes, it's the between the reactants and the products. It looks like Kabiro is going for reactants and products. You're right, Osharika. You're all right. Well done. It's between the reactants and the products. And finally, whoops, it says and exothermic. It meant to be an. An exothermic value is given a negative or positive sign. Exothermic, is it negative, negative, or positive? Negative or exothermic. Exothermic, exit given out, heat given out. Is it negative? Well, we're only very definite there. Whoa, hang on, he's changing his mind. Oh no, oh man. Never change your mind. Don't change your mind this time. Exothermic, negative or positive? Negative or positive? Well, it's negative. It's because it is lost from the reaction. Okay, it's given out. Wow, that's a nice sound. Okay, so on we go. So here's a bit more knowledge check. Here is a question. Excuse me. Use the data underneath to find the enthalpy of formation for ammonia. That's from nitrogen hydrogen to ammonia. So that is that equation there, okay? Now you are given some data underneath, and what I'd like you to do is to try to think how it might be used. I'm going to help you. I'm going to help you because it's too difficult as it is. I'm going to help you like this. So I'm telling you that the thing at the bottom is 2 NO and 3 waters. So if you want to start constructing it from there, I want to know what this is up here, the red arrow. So if we think Nairobi, Malindi, here's Nairobi, Mombasa, Malindi, you can put these numbers like 181 will be for nitrogen and oxygen to make 2NO. In other words, from here, top left, down to the 2NO down here. Okay, so from N2 to 2NO here, that one will be 181. Okay, so have a go. Stretch yourself a bit, have a go, see if you can do it. Remember that if you have more than one of the chemicals, like 3H2, you will need 3 times negative 286. Just have a go. See if you can do it. So just have a go, see if you can do it. It's not easy. You have to understand what is happening here. If you're not quite sure, Kabiro, I will help you in just a minute. Or Wamuini. Some of you are very, very clever, I know. But if you don't know the method, it's not easy. So I'm just going to help just a little bit. You're going to have arrows like this. Okay? You're going to have arrows like this. This N2 to 2NO will be worth positive 181. Okay, that arrow there will be worth 181 in that direction. Try and work out what 3H2 to 3 waters is worth if 1 hydrogen to 1 water is negative 286. So that arrow there, what will that be? And this one here, in the equation, it says 2NH3. That's 2NH3 here. So it's only one of these, negative 587. And then one of the arrows needs to change. Okay, one of the arrows needs to change. Just have a go now. Anybody get an answer so far? Wow, we've got an answer already from Usharika? No. Well, let me see. You've done some of it right, but you've not changed one of the arrows properly. Just remember on these that the route across the top here, let's see if I can write on it. So this one here, this delta H here is the same as going from here to here all the way round, from up here all the way around there. Okay, so if this, for instance, this arrow, where am I gone? Oh, I've lost this arrow here. This one here is is 181. This one here is 3 times negative 286. This one is only 1 times negative 587. But I'm going to have to change the right-hand arrow. Okay, to go up, I'm going to have to change the right-hand arrow. The number that you should come out with is quite small and negative. Anybody got an answer? Oh, yes, Dandora. Name, please. Oh, St. Mary's. Oh, not quite St. Mary's. You've got, what have you got wrong there? 758. Well done, Celine. No, it's not 2 times the 587. It's not 2 times the 587 because in the equation, it says 2NH3 and at the top it says 2NH3. Let's have a look, Mathari. I can't see it. Ooh. Hang on. Up a little bit. Yes, well done, Mathori. Who's that, please? I've got Celine so far for the gold medal, but you've got the silver medal. Mathori has the silver medal. And who in Mathori has the silver medal? Come on, Glory, you can get the bronze. Come on, somebody else have a go. Joseph, I think it said, hold a bit still. Yeah, well done, Joseph. Well done, Celine. Well done. Oh, and wow, is that Kabiro? That's 3 answers, all correct. All correct. Osharika, no, not quite. You've added it all together. Right, let's have a look at the answer so everybody can move on. So, whoops, sorry, what's happening there? Oh, I don't know why this is not writing. Sorry, let me just come out of this. Hang on, I have to come back to it. Okay, so let's see if I can draw on this. Okay. So this arrow here is positive 181. This arrow here will be, because it's 3 hydrogens, will be 3 times negative 286. This one here, although it is 2 here, because it is 2 in the equation, is negative 587. Now, if this here is the same as all the way around here, I have to change this arrow here. And therefore that becomes positive. Okay? And that means then that the whole thing looks like this. That's 181 and 3 times negative 286 and positive 587, which is negative 90. Well, there were, I remember Celine and Joseph came first and second there, which was brilliant. Well done. Really, really good. So let's move on. Now, here's another one. Oh, Glory, problem?
I'm not understanding. Can you repeat again?
I can. Yes.
You pardon.
Okay, let me just... Glory, I'm going to try to repeat, but you need to mute. Thank you. Okay. In these equations here, let me just get rid of all this ink. In these equations here, the root across the top is the same as the root round the side. So in other words, from here to here is the same whether I go in one direction or down here and then up there. The total is the same. The difficulty is that some of the time the arrows, for instance, this one here is in the wrong direction, and so will need to be reversed. When we reverse an arrow, we change the value. Okay, so let's have a look at it. So I'm now going to put the values on this. Okay, so let's see if we can do it a bit better. So from nitrogen, this is I'm going to call this equation 1, equation 2, and equation 3. Okay. Equation 1, N2 plus O2 goes to 2NO. That's the same as this arrow here. That is positive 181. This here, so that's equation 1. Equation 2 is hydrogen making water. This is this one. Equation 2, but because there are 3 of them, I need 3 times the amount of energy change, which is negative 286. For this one here, this is equation 3, because it starts with 2 ammonias in here and 2 at the bottom here, we only need 1 of that energy, and that is negative 587. So if we take the numbers which we've got 286. Then I end up with my total answer will be 181, which is positive, plus this is 3 times negative 286 is 858. That's negative 858 plus this is going to change direction, and so it changes sign, positive 87, and that comes to negative 90. That's how we get there. Okay, I hope that's a little bit better, Glory. Let's move on. Here is another bond energy chat. Have a go. Okay, so here is the equation. N2 plus 3H2 goes to 2NH3. This is what it looks like. So I'll give you a moment to calculate that. Remember, Bendo, Mexo. In other words, everything, if I make it, everything to the left of this, everything on this side will be Bendo, in other words, plus, and everything on this side will be Mexo, in other words, minus. Okay, so add up all the bonds on this side, they're all going to be positive, on this side negative, and then total them. Have a go. Everybody have a go. Come on, Glory, you wanted a bit of help, now you can have a go yourselves. You students are working very well. I'm really, really impressed. Thank you very much indeed for taking part in it. I do appreciate it. So there it is. Everything on the left, everything on the right. Well done, Dandora. Is that Celine again? Well, Celine, you are clever. Well done. Oh, so Mary's, have you got an answer? Not. Okay. So total the whole lot. I don't think it's not on the Mexo. It's not 2 times 389. If you look at the whole molecule, there are 2 molecules, but there are 6 bonds. Okay, 2 molecules with 3 in each one. Have a quick another go, St. Mary's. Look at 2NH3. Each line needs to be made. So it's 6 times, not 2 times. 6 times, not 2 times. Okay. You're doing really well, guys. We've already got a correct answer, which is fantastic. Come on, Wanweenie. You deserve silver or better. Come on, Church Army. I haven't seen a single answer from you today. I'm very surprised because normally you're very, very good. Mathari, you have an answer? Mathari has an answer. Mathari has an answer of you. Wow. He's a guy, Joseph. Joseph and Celine today have done incredibly well. St. Mary. Oh, okay. So what's the total? Up a bit. So you have to total those 2 numbers, St. Mary's. So add 2240 and negative 233, whatever. Just put the 2 numbers together and tell me what the answer is. So you put in whatever the answers are, whatever the numbers are. Add those 2 numbers together, St. Mary's. Just add them together. Okay. Oh, Church Army. Church Army has an answer. A bit closer, please. Hang on, let me just make it a bit bigger. Well done, St. Mary's. Show me again. Up a bit, Church Army. Yes. At last, everybody's getting courage. Thank you very much. So here it is. The answer is negative 94. The answer is negative 94 because it is one nitrogen triple bond nitrogen, which is 944, very, very strong bonds. It is 3 hydrogen to hydrogens. Then we make 6 nitrogen to hydrogens. Okay, nitrogen to hydrogens there. Total negative 94. Okay, so we're finished that particular bit for today. That particular bit of it. We now have the new topic, and there are only 2 parts left of energy. Okay, only 2 parts left. The first one is about latent heat. Latent heat is very important. It's something that there are lots of questions about, but they're really easy. That's about the change in physical state. So you know that you have to heat up water to boil it. You know you have to cool down water to turn it into ice, and so on. And it's about those changes. So that's what we're going to do now. We're going to look at latent heat. If you want to take notes, you can, but this PowerPoint, this presentation, I will be sending to your teachers. So if they want, they could print out the proper pictures or show you it again, whatever you want. And as I said, this is recording, so you can see it again if you want. Not many people do want to see it again. I don't blame them. Right, so here we go. So I'm going to share my screen, and we're going on to latent heat. And here we go. Come on, slideshow. Okay. Oops. Okay. So latent heat. Latent heat is all about the heat changes when changes of state happen. They are physical changes. We do not use the word reaction. That is really important. When water turns into ice, or ice melts, or wax turns from solid into liquid, we don't say it's a reaction. So you must not use the word reaction. You have to be able to name and describe the physical changes. So you have to be able to say what happens to the particles when ice melts and so on. You have to say what happens to them in terms of how they are arranged, their energy, and their movement. Okay? Their arrangement.
Excuse me.
Guys, thank you. You have to describe the particle arrangement, the energy, and the movement. Hi, guys. Have you got a problem? No? Okay. And diagrams can be very useful here. So that's what you have to be able to do. You have to recognize that they are all physical changes. They are not reactions. And you have to be able to name them and then describe what is happening to the particles. So here we go. Here is a sort of diagram. Oh, why is that sideways? Very interesting. Okay. So we are talking about energy up the side. Okay, energy up the side, enthalpy or energy up the side. And the least energetic is solid. And then it is liquid. And then it is gas. And something you really don't need to know about, but I have put it here for those people who are interested, is plasma. Now, you should know these changes. I don't think there's any need to draw this because you know these names. You know, like if I take from solid to liquid, you know from solid to liquid is called melting, and from liquid to solid is called freezing. You probably know that liquid to gas is called boiling or vaporization, and from gas to liquid is called condensation. You may not know these two. From solid straight to gas and back. From solid straight to gas is called sublimation. Sublimation. And from gas straight to solid, it's called deposition. So if you take gaseous carbon dioxide and you turn it straight into a solid, if you cool it down to -78, it will turn into a solid. And that solid, dry ice, that has been deposited. Okay, when it re-evaporates, it isn't evaporating because it doesn't melt, then evaporate. It sublimes. So there are some words which you need to know. Okay, freezing, melting, vaporizing or evaporating or boiling and condensing, and subliming and being deposited. Give you just a moment if you want to write that down. Okay, moving on. Okay, now this is important. If you've got a phone, you could always take a picture of this, but I'm going to just talk it through because it's important that you can do this. So we're going from solid to liquid to gas across the top, and I'm going to start with the pictures because I think most of you are aware of this. Firstly, in a solid, the particles are very close together and they are vibrating on the spot. It's not a very good picture, but it may be that it's easier to see. Whoops, hang on. Oh, Lord. Where's that gone? Right. Here it is. The solid particles are very close together and they are just vibrating. In the liquid, they are still very close together, and that's important. They are still very close together, but they are not organized. They are free to move through the through the liquid, and they are free to move quite quickly. In a gas, unless they are trapped, like in a balloon, they are much further apart, something like 10,000 times as far apart as in solids and liquids. So in the solid, they are very close. Oh, and this is a mistake. In a liquid here, it says far apart. This is something which came from a KNEC, the National Examinations Council textbook. This here, far apart, is wrong. Liquid particles are close together. Liquid particles are close together, okay? So it's very important that you know that this box here is wrong. They are close together, okay? Guys, please mute. Thank you. Please mute.
Silver still mute.
Somebody mute, please. Is that Silver Spring? Right. So that second
mute,
box there.
please.
Okay, guys. Good. Now the solid, it is basically they are shaking quite slowly. They don't move out of their position, so they are located. Liquid, they are free to move in the liquid, okay? Much faster than in the solid. They are free to move, and I think it is worth saying here that they are random movements, okay? Random movements in liquids. And in gas, extremely fast, and again, it is random movements. In the solid, the force of attraction in solids, liquids, and gas is the same, but In a solid, they have a very high ability to attract because the particles are moving only very slowly. In a liquid, they have a lower ability because they are moving faster. And when they're in a gas, there is effectively no attraction between them. No attraction between them. We will, in the Bendo Mexo, we will revisit it again next time. I'm sorry I didn't see your message. Bendo Mexo is just a way, if you go back to the recording from last lesson, you will see what Bendo Mexo means, but basically breaking bonds is always endothermic and making them is always exothermic, and endothermic are always positive values and exothermic are always negative. So if we look at the molecules and we add up all the bonds which need to be broken, you add them all up as positive values. And then you add up all the new bonds and they will be all negative values. And then you add the two together. So in attraction, the force of attraction is the same, but because they are moving faster in a liquid or a gas, they don't affect. I'll give you an example. Let us say that you are in a crowd of people and somebody holds you and the crowd is very, very close together, like if you're at a football match or something, and somebody holds you while you're in that crowd. Because there are many people around you, this is like a solid, you can't move, and the force with which the person can hold you is strong. Now let's change that and let's make it much more open. Let's say you are one of the players on the pitch and you are running. Now, if somebody tries to hold you, they cannot hold you because you are moving quicker. So the force of attraction, the person's strength is the same, but because you are running now, you are now in a liquid, like in a liquid. Now they cannot hold you. Now I want to imagine that you are in an aeroplane. And the other person is on the ground and you're going to fly past them. They still have the same strength to hold, but can they hold you if you are in an aeroplane? I don't think so. So in a solid, the strength is the same as in the liquid or the gas, but in the solid, it is like you are really close together and their strength is good. When it is a liquid, you are moving faster, like you are the football player. You run past somebody quite quickly. In liquid, their strength is not enough to hold you. Now in a gas, it is like you are in an aeroplane and you are going past them really fast. They cannot possibly hold you. So although the force of attraction is the same, it is not so effective. That is what it is. Okay, so apart from the error at liquid, with the far apart in the liquid, which is rubbish, as you can see from this. In fact, if I was going to redraw this gas here, let me just redraw the gas. So I'm going to pop the balloon. Here is one particle, okay? I'm just going to put it here. Here is one particle of gas, okay? Here's another particle of gas. Oh, it's moved. It's right over here. Here's another particle of gas. It's right over here. Here's another particle of gas. Oh, it's right over here. In other words, they are a long way apart. Here's another one. They are much, much further apart, okay? The distance between particles in gas is much greater than between those in solid or in liquid. These two are quite similar, okay? In solids and in liquids, they're quite similar. Okay. This is a graph to show a particular chemical. It is not water. And this is what is happening when it melts and boils. Okay. It's quite important that you see this as an idea. This one here is water, and this is the one we're going to look at. Okay. But I want you to see they are all the same shape. This is not water. This is. So if you're going to draw any one of them, I suggest you draw this one. But there's a bit missing from it. And that is up at the top. Oh, I can't move myself. Why not? Okay, you can't see properly on mine. I'm just going to have to draw something on the end of it because my little picture is on top. So in other words, what I want you to do is up here, I want you to draw another line up here, not this one here. Just draw a line. So just take the line from here and draw it up like that. Okay, so it carries on up. So not the bit along the bottom. Okay. Things to notice. Firstly, the graph has temperature up the y-axis, up the vertical axis, temperature. Along the bottom, it has either heat added or it has time. It doesn't matter which one it is, time or heat added. And we assume that we are starting with, for instance, a beaker with some bits of ice in it. And the bits of ice have been taken out of a freezer. Okay, and I'm going to put it on a tripod like this, and I'm going to heat it. But it's going to start at, so if I have a thermometer in here, this thermometer is going to say it's minus 50 degrees Celsius to start with. Okay, minus 50 degrees Celsius. That is really cold, but that's in a good freezer. And as I heat it up, what happens is that it follows the line. So it goes up here, up here, up here, okay, all the way up. I hope you can see my pen up the side. Let me just see if I can change the color of the pen. Can I change the color of the pen? Why not? Come on. Okay, let's see if we can see this. I don't know if we can see it any better. No is the answer. Okay, doesn't matter. So up we go. So it's going to follow this line up here. And the temperature will go from minus 50, minus 25, and 0. And then for some reason, all the heat does not raise the temperature. And what is happening here at B is that the heat is going to smash up the ice cubes and turn them into a liquid. So all of A is solid. All of C is liquid. All of the time up here, it's a liquid. But in the bit between at B, it is a mixture of solid and liquid. Okay, a mixture of solid and liquid. So if I was going to label these, let me just see if I can change my color again. It's better with it was before. Sorry. Oh no. Gee dear. Okay. So I'm going to I'll show you what I'm talking about in a minute. Sorry, I'm going to have to stop sharing and come back. Annoying. So here it is. And we are going from here down at the bottom. And we're going to follow it up all the way through A and then up across B and up C and across D and up to E. Okay. So if you're drawing this, the horizontal lines are at 0 and at 100. 0 is the melting point of ice or the freezing point of water. They're the same, aren't they? Okay. So in other words, we've got there at that point, we've got something where we've got at B, we've got solid and liquid together. Solid and liquid together. Why does my pen not work today? Come on. Okay. So A is all solid. And C is all liquid. But B is a mixture of solid and liquid. Then the liquid starts to evaporate here, or boil, in this case boil. And so up here we have a liquid and gas. And then beyond that, it is all gas. Okay? So that's what it looks like. So what we would see is bit by bit, all the solid would melt down until it's a liquid. And then the liquid would evaporate, okay? All evaporate, boil off. And that's what's happening during the process, okay? Okay, I hope that makes a bit of sense. So the question it often asks, the sort of question they ask is, what is happening at A? What is happening at B? What is happening at C? What is happening at D? And what has happened to temperature? What has happened to the particles? Are they further apart, further together, and so on? We go back to the last one. What is the melting temperature of this chemical? Well, all we do is we look for the first horizontal line. That's where it is turning from a solid into a liquid, and it's at -60. So whatever this is melts at -60. And whatever it is boils, that horizontal one there, at about, well, it's just over +60. So that's how we read these graphs. We're looking for the horizontal ones to read off the melting and the boiling temperatures. Okay? It's fairly straightforward. Okay. So would this particular chemical be a solid, liquid, or gas at room temperature? For that, you need to know what room temperature is. And room temperature varies. But in a textbook, they normally say that room temperature is about 25. Now, often it will be hotter, but they say 25. So what I do is, if they say, is this chemical a solid, liquid, or gas at room temperature? I start at -100. I go, hey, it goes up. Or I know it is melting at -60. Then I draw a line at 25, approximately. And I know here that the line, okay, this is all solid. This is solid and liquid. In C, it is all liquid. So the answer is, at room temperature, this chemical is a liquid. Okay, this one is a liquid. That's fairly straightforward. You're just looking at what would happen. Now, I'm going to go back a couple of slides. When I'm going to go back here, I'm going to say, what state would it be at -20? What physical state would this chemical be at -20? How would I do that? Well, all I would have to do is to draw a line across at -20. So I find -20, I draw a line across. This is C, this is a liquid. What would it be at -80? Oh, well, -80 is down here. That there, that is solid. This here is liquid. What would it be at 100? Whoops, nearly straight across. E, it would still be a gas. Okay, so that's what you do in these questions. Okay. How are we getting on? That's the end of the lesson for today. I'm sorry that it's the end of the lesson for today. I hope it's been useful. Whoops.
We have a question.
You have a question? I'm glad you have a question. I will wait for a question, but I'm going to stop recording now. Next time we will be showing how